programming. Yeah. Let me see. Yeah, I'm the one who's a bit perplexed now. I have to think now, 40 years ago, I was a student of physics, and I was learning quantum mechanics. And there was a guy, Professor Burrop, and he said, it must be very difficult to learn quantum mechanics, because I've been doing it for 50 years. And the advances in quantum mechanics, they were pretty slow. There'd be a new advance, and I would learn something, and I'd have a few years to accommodate those ideas. And then there'd be a few more years, and a new result, and I would learn about that stuff. And he went to the Cavendish lab in 1933, and Lord Rutherford was his advisor, the guy who discovered alpha and beta radiation and the father of nuclear physics. And he said, I don't know how you can learn all this stuff in a couple of years. It's far too much. And that's kind of what I think now. I've been programming for 50 years. And, well, when I started, there wasn't much stuff. And, hello, let's press this. Shouldn't this go forward when I press it? No. Hello. Ah, good. Yeah, well, computer science is confusing because it's not a science. And there's an awful lot of stuff floating around. And I say, well, you know, the latest stuff, that's not computer science. Right. Huh? This thing. You know, I was a professor of fault-tolerant computing, which is why I don't trust these things. And it doesn't go forward when I press the button. Should I, like, wave if I want it to? It's the green one? Yeah, it's the green one. Look, I press it and nothing happens.
How about this? Just say slide and we'll dance it for you.
Okay. Well, actually, it did move then. I'll say, I can't say. I'll say the last word. I'll say, if I wanted to move it. So what are my goals? Hang on, no, it doesn't work. It doesn't work. I told you it wouldn't. Oh, sorry, never mind. Slide. Right, okay. Oh, no. You know, my wife says, why do you print your tickets out on paper before you fly anywhere? Why don't you use this app on your mobile phone? And I say, well, it's because I'm a professor of fault-tolerant computing. Why do you think? Okay, so what I want to do is identify some problems worth solving and identify some stuff that's worth learning. Oh, thank you very much.
Push it real hard.
Right, okay. Yeah, okay. Well, let's do a test. Brilliant. Brilliant. Thank you very much. Okay, so 50 years ago when I started programming, there wasn't much software. So in principle, you could learn everything there was. When I started programming, I was given the choice of learning Fortran or nothing, because that was the only choice there was. And so I learned Fortran. Things are slightly different then. The turnaround time for a program was 3 weeks. 3 weeks after you'd written your program, you got to see the first syntax error in it, because the Fortran compiler stopped at the first syntax error and didn't go on to the lines that followed the first error. And so once you got your program back, there was another 3 weeks delay, and you could resubmit it, and you get to the second error in your program. That made debugging difficult. Of course, there were no debuggers, so that made it even more difficult. But it did teach you to stare at your program before you submitted it, and not after you'd submitted it. Well, now the program compiles during the time that the spring underneath the enter button recoils, so it's pretty quick. 25 years ago, 30 years ago, it was about right. There weren't that many programming languages, there weren't that many operating systems, so in principle you could understand more or less everything, really. Maybe not everything, but you could understand a large proportion of everything that existed. And now there's just far too much. I mean, there's a heck of a lot of stuff. I would, if somebody said to me, you know, I'm just learning computer science, what should I learn? I'd say, yeah, well, you should learn this. And actually, this talk is about that subject. What should you learn? Because a lot of people say, what should you learn? And I'm thinking, yeah, I'll kind of reflect on what I've done. And it's very biased. It's the stuff I've learned, stuff I've had use of. So I thought I'd tell you guys. Right, so there's also this set of gaps. There's the problems that computer scientists study. And I was looking at this and looking at the thesis topics and say, so what's the hot stuff in computer science? What are the research topics? And I was making a list of them. And then I thought, I'll ask my neighbours in the apartment where I live, and I say, so what problems have you got? And is there any intersection between the problems that computer scientists study and the problems my neighbours have? And I think the answer is no. You know, there's absolutely no. You know, my neighbours have completely different. You know, their computers don't work, and they don't know why. And actually, I don't know. I mean, I stream movies, for example, with Netflix, and most of the time it works fine. Or I listen to music with Spotify and my Sonos system. So when I'm listening to music with my Sonos system, it will work for an hour at a time beautifully, and it'll suddenly stop. Oh! And I can't, you know, right in the middle of a Chopin waltz or something like that. It's just, I think, what the hell has happened? And I don't know who to complain to. Do I complain to Sonos, your software's fucked up? Do I complain to my ISP? Has DNS failed? Has the modem failed? And then I go through I do what I tell my neighbours to do. If the problem won't go away, the one that most often works is rebooting the modem, the cable modem. Okay, I've got 100 megabits per second, fibre to the home. It should be great, but it just stops. And I don't know why. And I'm a professor of computer science, and nobody on the planet knows why. Well, perhaps somebody in this room knows why. You know, catch me a coffee and tell me, because I'd really like to know. And then there's the problems that industry solves. Now, what problem does the computer industry solve? It solves the problem we want to make loads of money. They basically don't care about computer science, and they don't care about the users. What they care about is making loads of money. And all of these are completely different. Also, I just kind of noticed that there's a sort of gap between the software that we can write and the software that we can understand. And a few years ago, that gap was, no, I backtrack, that's not true. There's always been a huge gap between that, and that is largely due to mathematics. So let's take a really simple problem, the 3n plus 1 problem. If n is odd, replace it by 3n plus 1, and if n is even, divide it by 2. And the Gollancz conjecture says, well, this process will eventually reach the number 1 for all starting values of n. And it appears to be true, and nobody's managed to prove this. If you write this as a program, it's a tiny program. It's a trivial program. But the properties of that program cannot be proved. And so Pearl Erdos says mathematics may be not ready for such problems. So deep down in software, there are fundamental problems of mathematics that we do not know how to solve. And indeed, Gödel says that mathematics is decidable or inconsistent, or it's either inconsistent or undecidable. And I guess programming is both undecidable and inconsistent, so it's kind of fun. Okay, so back in this lecture or talk is done in three or four parts. Back in the 80s, I had a plan. That was how to find things, how to store things, and how to program things. And I kind of thought about that a bit. And that boiled down to some sub-goals. Learn Emacs, learn Unix, and learn a programming language. That was my answer to how to do the first three things. And what actually happened? Well, there's been a little bit of progress in all these areas. Finding things, yeah, there's been a bit of progress. Google and friends have made search engines so we can find things. We usually find the wrong stuff, but it doesn't matter. We save things. there's a small amount of progress there. Dropbox can save things, but not forever. Dropbox will save things as long as your credit card keeps on the payments, so we don't know what's going to happen to that stuff in the future. And one of the things that concerns me and concerns a lot of people is what will happen to our history. You know, in 200 years' time, will people be able to find the photos we've taken today, or will they have all been put encrypted in the cloud and be inaccessible to people in the future? It might well be that it will be as difficult for us to know what happened 200 years ago as it is for us to know what happened 1,000 years ago. It's rather a shame, because if we're going to learn from our mistakes, we need to record our history, and we need to be able to see it in the future. Programming things, has there been any progress in programming in the last 30 years? Not much, actually. A few little small things. I don't see any really big breakthroughs. Prolog was the last thing that was radically different to the things that came before it. I don't really see things. Oh, maybe dependent types and things like that. Right. Okay, so how did the idea for this talk start? Well, about 2 years ago, I had the privilege of interviewing Alan Kay on stage at Code Mesh in London, and I thought, oh, what do I ask? What do I ask him? So I thought I made up some questions I was going to ask him, and one of the questions was, what are the great ideas of computer science that we've forgotten? There were a lot of good ideas in the 60s and 70s. Some of them have evolved. Others have just been completely forgotten. They're still waiting to be resurrected. So I asked him this question, and we talked about that. And then I tweeted, I'm interested in the forgotten ideas of computer science. Twitter's great, you know. The next day, I had 277 replies, which I printed them out, were about 40 pages of PDF. And I started looking at that. So I started making some lists. Now, lists are very easy things to make. But the trouble with lists is that you have too many items on the list. Right, there we go. No. There, yeah. So the easy thing about a list is making lots of points in the list. The difficult thing is removing items from it to reduce it to a very small list. So I made a lot of lists about different areas of computer science. And I'll give you an example. Suppose your professor makes a reading list of books that you're supposed to read as a student. Well, it's quite easy to make a list of 15 items. And of course, the teacher's done a good job. And of course, the teacher also knows that the students will not read 15 books. If you're given a reading list of 15 books, you're not going to read 15 books. There's just no way you're going to do it. So what I thought, I'm not going to give you lists of 15 books to read. I'm going to give you a list of 3 books to read. I think if you reduce these lists, it's a way of taking responsibility. And that's the difficult thing. It's throwing your babies away. I made this nice list with 15 books in, and now I have to remove them to a small enough number that you will remember that, and there's a chance you might read them. That's a very difficult thing. And it's one of the things I do a lot. Whenever presented with a list of lots of things, it's a good thing to ask which is the most important item on that list. When I was working for Ericsson, 5G systems were very popular, and a new project manager rushed in and he said, 5G's going to do remote medicine and driverless cars, and he had a list, he had like 45 things on this slide, and I said, what's the most important thing? He looked at me strangely, and I said, well, look, I can only do one thing at a time. You've got 45 things on this list. I can implement the most important thing. Which is the most important thing? And he said he didn't know. So I said, well, I don't know what to do then. So whenever you see a list, and whenever you're in a project, and there's 20 items on that list, just tell them I can only do one thing at a time, and ask them which the most important thing is. And if they can't answer, get a new project manager. So this talk has emerged into a kind of list of lists, because it is a guide to the confused, and it is what I think you should learn. So I made some lists, and there are a total of 80 things. It's quite a lot, actually. This is a guide for the perplexed. I mean, I've got it down to a mere 80 things from, must be thousands of things. And it's very personal. It's stuff I think's good. So 2 great papers to read, and 4 old tools you should learn, and 3 great books to read, and so on. I've given this talk twice, and afterwards I got some tweets saying, hey, I read that paper, you said it was really great. I said, have you read the other one? No. And they read the other one. I said, yeah, that was great as well. And there's some fun stuff as well. Right, so let's... oh, and the forgotten ideas, that was kind of, whoops. Oh, can't go backwards, never mind. Okay, 2 great papers to read. A Plea for Lean Software by Nicholas Viet, and The Emperor's New Clothes, the ACM Turing Prize lecture by Tony Hoare. Anybody read any of them? Nobody, that's wonderful, that's great. Oh, yeah, well you would, wouldn't you? Dave Thomas has, of course, read all of this stuff. And you'll have read all the books as well, won't you? Well, you don't know what the books are going to be, but you'll have read 2 of them. Yeah. Okay, so these are really good papers, and Nicholas Viet says, in the middle of his paper, the belief that a complex system requires armies of designers and programmers is wrong. A system that is not understood in its entirety, at least to a significant degree of individual, by a single individual, should possibly not be built. He also says to gain experience, there is no substitute for one's own programming effort. Organizing a team into managers, designers, programmers, analysts is counterproductive. I'm a full-stack developer. I develop the language, the frameworks, the libraries, and everything. I didn't write the operating system. That's a flaw in my... It's a kind of... And what did Tony Hoare say? He said... you should read this paper. It's really readable. He said he was in charge of this project and it went wrong, and the managing director of the company that had sponsored it stormed into his office. This was a manager who knew nothing about software at all, and shouted at him. He screamed at him, and he said, you know what went wrong with your project? And Tony Hoare was, because he's a mild-mannered man, and he said, no. And the manager said, you didn't understand what your people were doing. And Tony Hoare thought, hang on, this guy is not a programmer, he's a manager. How on earth does he, how can he make statements like that? And then he realized later he was right, because the manager said, that's the reason why projects always fail, that people don't understand what they're doing. And if you're ever in a big project, and you're trying to find out how it works, and you talk to people, and they say, well, no, I don't understand how this works, but somebody else understands how this bit works, then you can be sure that you're in a project that's going to go pear-shaped and not work. So really, you've got to find somebody in these projects who understands how the stuff works, otherwise it's just not going to work. Okay, 4 old tools to learn, Emacs or VI. I'm not religious about these things. I belong to the true church of Emacs, but some people say VI is good. A good text editor that's small and fast and customizable. Bash is the only scripting language you ever need to learn. Make is the only build tool you'll ever need to learn. And just how the shell works, just a terminal shell. And I would really recommend using Make. I cannot understand why people use specialized build tools for their different languages. I mean, it's fine. You're using Malvern or something for Java and Groovy on Jails or Rails or whatever the bloody thing's called. Grumpy 2 or something. And they've all got different build tools. Well, why bother? I mean, you can use Make for everything. Once you've learned how Make works, you use it for everything. And then you don't need to learn a new build tool when you change your programming language. It's very easy to learn as well. Right, 4 really bad things. Lack of privacy, attempts to manipulate us through social media. Vendor lock-in, that's a really bad thing. Should be aware of it. I mean, the world is full of these JVM people, JVM, and .NET, and Linux. And so we implement everything 3 times instead of once, which of course is very good for the vendors, but not very good for everybody else. Oh, and terms and conditions. I was just going to write. Right, hands up everybody who's read all the terms and conditions and understand them. Nobody, right, God. Okay, yeah. Hands up everybody who just clicks on accept as soon as terms and conditions comes. Right, like me, yes. Like the rest of the planet, actually. Why do they have, I mean, if I buy a chair, this bottle does not come with terms and conditions. You have to read the terms and conditions. It might contain water. It might be a quench thirster. It's mad. We've got to get rid of software terms and conditions. Fucking, it should just work. Just work, I'm sorry. Okay, 3 great books to... Dave, you've read 3 of them? 2 of them? You've read 3 of them, I knew, yeah. Okay, so the one book of computer science you have to read is Algorithms plus Data Structures equals Programs. Why should you read this? Nicholas Wirt is, in my opinion, the greatest programmer ever. I mean, he's the only person who has made a programming language, an operating system, and the chips. He's done the hardware design. He's designed the chips. He's made the operating system Oberon, and he's made the programming language Pascal, which evolved into Modular 2, which was used to program Oberon. And in this book, he describes the theory of LL1 parsing and how to go from diagrams to a byte-coded virtual machine, and he describes the interpreter for that virtual machine. That's the P-code machine. The P-code machine is the precursor of the JVM and the .NET virtual machines. Basically, the .NET virtual machine and the JVM are very, very similar byte-coded machines. Once you've understood the P-code machine from Wirt's book, you will understand completely how these things are engineered. The one in the book is a deliberately simplified version. It's got about, I'd guess, 35, 40 opcodes and a very simple implementation in Pascal. It's a very good book. The Mythical Man Month is the one book you need to read about software engineering. Brooks worked for IBM, the project manager on the IBM 360 project, which was delayed by a very large amount. And Thomas J. Watson asked him why was the project delayed so much, and Brooks said, well, I've got to write a book to answer that. So, and he came up with some quite key ideas, I think, in software engineering. One of the major ideas that comes from the book is that of partitionable and non-partitionable tasks. And he points out that if you want to have a baby in 1 month, you shouldn't get 9 women to do it for you. Having a baby is a non-partitionable job, which takes 9 months. You can't get 9 women and do it in a month, and you can't get 18 women. And the software industry seems to think we can partition programs by getting whole teams of programmers, and it'll go quicker. And in fact, it goes slower. So that's a really good book. And, well, the third one is this Dale Carnegie, How to Win Friends and Influence People. If you're programmers, you not only have to write code that works, you've got to persuade people to use your code. If you want to start a company, you have to talk to venture capitalists, you've got to talk to people. And this is all about the interactions between people. Dale Carnegie was a salesman. He studied the works of... He sat down and said, how do I become a great salesman? And he went to the library and he read what Lincoln had written, he read what all the great statesmen had written, and he kind of encapsulated all this knowledge and wrote it in this book. This amazing book. Anybody read it? Yeah, it's good, isn't it? Tell the other guys it's good. You should read it once a year because you forget. And it's the techniques are very powerful. I've done some of these things myself. And, it works, it's good stuff. Right. So 7 reasons why software is difficult. Well, we are plagued with fast machines and huge memory, hundreds of programming language, huge programs, no specification, and reuse. My goodness, don't all these things make software difficult? I mean, if we didn't reuse any software, we had to write it all and understand it, well, our systems might be cracked. Every time we reuse something, we inherit all the bugs in the stuff we reuse. Of course, we're not aware of that fact. It's rather difficult. There are hundreds of programming languages to choose between. And of course, very fast machines hide very horrible algorithms. Having loads of memory means you can write any bloody crap you feel like. Oh, and systems are distributed, so not only can you make your own mistakes, you can bugger up other people's programs, and their programs can bugger up your programs. Right. So 10 reasons why software was easier back in the day. Oh, it was great. We had small machines and small memory and few land. Oh, we didn't reuse code. We didn't have things like Xcode. And oh, wow, just imagine programming without Xcode, how blissful life is. We didn't have Git. We didn't have like Git blame and things like that. So we didn't keep the old versions of our software, so nobody could blame us when it didn't work. And we could understand our programs because they were small. Yeah, that was good. Let's click again. Oh yeah, this is kind of changed gear. This is one fun programming. Has anybody read this? You have. What? Yeah, you have. Of course you have. You see, the old guys, we've done all this stuff. So Dan Ingalls was the guy who implemented Smalltalk first. He said, do not read this paper. You do not want to read this paper. This is seriously bad news. If you read this paper, your brain will melt. So what happens when somebody tells you not to read a paper? It's seriously bad news. Do not read this paper. Yeah, of course you read it. This is the first meta system where it's written entirely in itself, and it becomes extensible. And your brain will melt and you'll have great fun. You can implement this in any programming language under the sun and just have fun with it, and it'll sort of evolve in its own way. It's really quite fun. A little bit of history. If you want to go into history, I have a different talk about history. These are some machines you might like to look at. On my holidays, I go around. I take my wife to computer museums, and we have a great time. We have a great time looking at early computers. And she goes like, oh yeah, is that? Oh yeah, that's interesting. No, this is good fun. This is, and the PDP-11. I have programmed all of these apart from the first and the last one. The NVIDIA Tesla P100 that's like 10,000 Cray 1s. I mean, it's ridiculous. This is the one that's going to make us obsolete. And the Cray 1, I mean, my little, this is a like 200 Cray 1s. The Cray 1 was the first supercomputer in the world. It weighed like 8 tons. It cost $8 million. I saw one at CERN. It was attended by serious-looking people in long white coats, lab coats, and you weren't allowed near it. You could. It's like a religious symbol. You went, it's a Cray 1. Oh. And now, somebody said, can you program Erlang on a Raspberry Pi? You know, a little low-powered computer. I said, hang on, a Raspberry Pi, that's like 8 Cray 1s. 8 Cray 1s. It's like 200 times more powerful than the computer we developed Erlang on. Of course you can do it. Of course you can do it. How can you make things go faster? Better algorithms. This is just what happened in my experience. If you get a better algorithm and you don't change programming language, you can get a better algorithm. Maybe your program goes 6 times faster. If you change programming language, you can go a lot faster. So when I was developing Erlang, we went from Prolog to C. I went about, what did I say there, maybe 50 times faster. But of course, these aren't the big performance gains. The big performance gains come from doing sod all and waiting. Because, well, Moore's law is applied, and it applies in different ways. It goes into the multi-cores in the future. But we get about a factor of 1,000 every 10 years. So you want your program to go 1,000,000 times faster, you do nothing, and you wait for 20 years. Well, it's easy, it goes 1,000,000 times faster. And then everybody says, hey, you're a really smart program, your program goes 1,000,000 times faster. No, it's the clock speed, it's the hardware, guys. If you want really fast software, don't bother changing languages, don't bother finding smart algorithms. Go find a hardware friend. Sniff around what the hardware guys are doing. And be on the leading edge with hardware. Hardware is where all the improvements have come from. Clock speeds of gigahertz, petabytes and zettabytes, and God, no, it's crazy. Right. Some five or more plus YouTube videos to watch. These are really good. This nice one, The Computer Revolution Has Not Happened Yet, Alan Kay. That's nice. It's a nice provocative title. I mean, everybody's thinking, hey, we've had this wonderful computer revolution. And Alan's just pointing out, no, it hasn't actually happened yet. You know, we're still waiting for it to happen. And who inspires Alan? Where does he get a lot of his ideas? Well, a lot of his ideas come from Ted Nelson. And if you Google, or you go to YouTube, and you search for Computers for Cynics, you'll find a series of lectures by Ted Nelson. And strangely, very few people have watched these. I mean, like 2,000 people have watched them. So it's not a lot of people watching this. So Ted is the guy who invented hypertext, and what we see in the World Wide Web is a kind of poor shadow of his vision of computation. There's some other stuff there which you can look at, but the big stuff, right? 6 things you shouldn't do: don't put backdoors in your software, and don't violate people's privacy, and don't put microphones in everybody's houses, and don't hijack our attention systems, and don't sell us crap that we don't want and we don't need. It's not much good. 5 sins: crap documentation, crap websites, crap dependencies, crap build instructions, and groupthink. None of you do this, I'm sure. I'm sure you all write beautiful documentation. I hear words of, no, I hear laughter in the audience now. 4 languages to learn. C, everybody should learn C and Prolog. They're very different languages. And I've even put Erlang and JavaScript there. Erlang's a little favorite of mine. Erlang combines object-oriented programming with functional programming. It sort of bridges these 2 little worlds. And of course, JavaScript is a very nice language. And people tweet, Armstrong said JavaScript. Yes, it is actually. It's great fun. I mean, it's got its little things. and you know, I've got quite a few grey hairs from JavaScript. But I've got even more from Erlang and Prolog and C. So I got a lot of grey hairs from C. Let's have a look. Now we're getting on to some forgotten ideas. Linda tuple spaces. This is the idea of a shared blackboard. You basically have a shared blackboard where you write problems, and you have a whole parallel sea of observers that are observing the blackboard, and they can just deterministically pluck off something and do the computation, write the answer back onto the blackboard when they've finished. So it's a very nice computation. It's a very nice way of parallelizing things. It was a very good idea. People do use tuple spaces today, but not as much as they should do. Then there's an idea, something called flow-based programming by John Paul Morrison. I see a nodding man in the audience. Flow-based programming is really great. It's a book which I think you can find free somewhere on the web. John Paul, he's pretty old now, and his ideas never really caught on. But they were great. And then Xanadu, Ted Nelson. This is the stuff. This is what the web should have been. This has been called the greatest vaporware project ever. I mean, like 50 years later, or however many years, it's still not completely implemented. I'll talk a little bit more about that. I say Unix pipe. Well, not really forgotten, but not really used. Let's see. So pipes. I just have a little mention about pipes. Yeah, the old Unix idea. The output of my program should be the input to your program. So we could just pipe things together, A pipe, B pipe, C, and text flows across the boundary. So this makes it very easy to connect things together. In particular, we can connect things together that are written in different programming languages, and it's very, very simple. This has been killed by GUIs because GUIs aren't text-based. GUIs are poke your little finger on the mouse and sort of click on something based. So how the heck can you pipe them together? Even worse, apps. Apps on your mobile phone and on your iPad are inventions of the devil. I mean, they're just not pipeable together. You can't take one app and pipe its results into the next app, and you can't just, apps sandbox you. They lock you into their little infrastructure. Oh, I've got this great photo editor. It creates a JPEG file or a PNG file. Can that file be used by another app? No way. No, you can't share data. Oh, no, that would be a security thing. So these apps lock us into sandwalls, into sandboxes, and make sure that things don't interact with each other. They even lock you into the platform. So, of course, your iOS apps that can't interact with your Android apps. So things should be pipeable together. They should be connectable. Right. Apps, yeah. Oh. And all apps, I mean, they're all kind of... I mean, don't get me wrong, some of the individual apps are very, 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 very good, and they're worth paying for. But none of them are perfect, They're all kind of lock you in. And can you program the damn things? No way. Oh, no, would they have a programmable interface? We've made supercomputers and handed them out to everybody, and then made sure that they're very difficult to program, which is tragic. Right, let's have a look. What have we got now? 6 areas to do research in. Robotics, AI, programmable, the robots are, I don't know if anybody saw the IKEA robot that can assemble a flat pack chair, which makes us wonder if this was the purpose of the human race, it's to invent a robot that can assemble a flat pack chair, and basically if robots can just make other robots using solar power or something, we can just, that's it. They'll be on the planet until the sun becomes a red giant assembling flat-pack chairs, and we'll have died out. Programmer productivity, yeah. I still believe, I still hope that we can improve the productivity of programming languages. Prolog and things like that are pretty damn good. Unfortunately, most of the languages that are commonly used and widely used today have their roots in about 1980, 1975, something like that. Things have actually progressed since then, but the best languages are not actually being used. Energy efficiency, we need to use our energy wisely. Precision medicine, this is coming on really, really nicely. I mean, I think analysis of our genome to find out which medicines we should treat various ailments with is proceeding at an enormous rate. So up to now, treatment of a lot of diseases is pretty haphazard. If you need to reduce your blood pressure, you don't really know which combination of drugs is going to work, but presumably we will know this fairly soon. And security, there's a lot of bad people trying to mess up with our world. So these are good areas to research. 2 danger. 4 ideas that were obvious now and strange at first. Indentation. This, I was reading my Daniel B. McCracken's Guide to Fortran 4. He hadn't, 2 ideas hadn't occurred to him. One was sorting the line number labels. The other was indenting the programs to denote structure. Very strange. Versioning, that was a neat idea. Putting a version number in. If you look at the RFCs for HTTP and things like that, they didn't have a version. Now it says HTTP 1.1 or HTTP 1.2 in the header. That's a relatively new idea. Nobody actually thought of doing that. So if you look at the history here, the first internet protocols had no name. They were identified by the port number. So you knew that port, whatever it was with mail, and port 80 with HTTP. And then they thought, oh, I know what we'll do. We'll stick a version number in a header. We'll say this is HTTP 1.1 or this is HTTP 1.2, and put it in the header. And that was version numbering. And of course, what's the next step? I mean, these version numbers are pretty damn silly because I mean, what does 1.2 mean? Well, the next step, which nobody's done yet, but I keep saying you should do, is in fact you shouldn't have a version number like 1.2. You should have the SHA-256 of the software of the server and the SHA-256 of the software of the client that has been known to work and been tested. Version numbers are not precise enough to guarantee that your system will work. So in fact, we should name all protocols by something like the SHA-256 or the SHA-2 or the MD5 of the code itself, not with some silly little version number. This idea of naming things by their checksums is commonplace in Git, but it's not commonplace outside Git. In fact, we should throw away all names and use cryptographic checksums to name things, and then life will be a lot easier. Well, of course it would. I mean, come on. You start naming things. So you want to name a file. You go, oh, what should I call this file? Oh, what directory should I put? Then you've got to name the directory. What directory should I put? What machine should I put it in? Just stick it all in the same directory. Just name it by its SHA, and then there's no problem. Pipes. Yeah, that was a silly idea. What else? Oh, yeah, this is fun time. Two programs that you really should try. They're similar in a way. Is Sam here? Yeah. It's good, isn't it? It's good. Tell him it's good. Yeah, it's brilliant, yeah. Sam wrote Sonic Pi. And to be honest, you would have more fun spending an hour with Sonic Pi or with the TiddlyWiki than listening to me for an hour. But you wouldn't know to run them. So please, spend an hour of your life playing with these programs. And then figure out how you can connect the TiddlyWiki to the Sonic Pi. In a way, they're very similar. Both of them are based on this idea of very small things that can be combined into bigger things. So Sonic Pi is based on this idea of very small fragments of code, which when you execute them play music, and they can be combined together in creative ways to create music. TiddlyWiki is based on the idea of small things that can be, it's a wiki. But it's probably the nearest thing you'll ever see to the old hypercard. And I'm going to talk about transclusion a little bit later. Ted Nelson would love this stuff. I mean, the TiddlyWiki is about the nearest you'll get to something that's half decent. It's very good. Right, part 3, how are we doing for time? When do I have to finish? 8 minutes, okay, right. Important non-computer science. I thought, this is my sort of guided tour of what you need to know if you're going to do computer science, be a programmer. And it's not just the technology, it's some other stuff. So, learn to write. A program with excellent documentation is not going to go anywhere. You know, the first thing I do when I go to a program, I read the documentation. If there's no documentation, I go, oh, okay, I'm not going to use this program. I don't want to read the code. Goodness, who wants to read code? I never understand it. And if I do understand it, I want to rewrite it, which is not very good. 3 rules that work. Rule number 1, if you get a bad boss, move immediately. Do not try and change them. I think this rule is not well understood. Everybody I know at a certain stage in their career will have a bad boss. Life's like that. You'll have lots of bosses in your life. Sooner or later, you'll have a bad boss. And everybody makes the same mistake. They think they can change their bad boss. And after 2 years, they'll give up. So if you get a bad boss, leave the next day, or maybe even the same day. I mean, don't let them fire you, you fire them. You just get out of there as quickly as possible. The next rule is, I worked with Jane Varlud who formed this company. Jane used to say, the relationship comes first. She majored in psychology. She was a people person and I was an engineer. And my idea of engineering was you sort of have technical arguments with people, and Jane's idea was, you become friends with them first. And how do you tell you to be friends with them? You've got to crush them with the technique, the power of your superior technology. That's what I thought. Until I was about 55 or something like that. And my world was, at the edges, was crumbling. Jane managed to get stuff done that I could never get. I'd won this argument. And they didn't do it. And Jane hadn't even had an argument, and they did it. And I said, how did you do that? She became friends with them first. Oh, that's a really weird idea. It's good. Engage with management. Just because management, you don't understand them, they're not like zombie. This is what, what's his name? Hamming said. He said, the biggest mistake in his career was the late stage. He was head of research at AT&T, Bell Labs, and he said the biggest mistake of his career was not to engage with management until very late. I think he did it like 5 years before the end of his career, or 10 years. And then he started talking to them, and doors opened. And I never really managed that. I think it was, I didn't really, I couldn't figure out what was going on in management's head, so I didn't talk to them. Not a good idea, actually. Right, distractions. Open plan, you know this, just open plan offices. If you're programmers, you don't want open plan offices. You can't get any work done in an open plan office. You get distracted all the time. And the latest stuff. Oh, got to learn the latest. Oh, no. No, just learn the old stuff and get good at it. Twitter and these links and things. That's why books are good. There's no links in them. You can't. Oh, look. Oh, who's getting divorced? Oh, I didn't know that. Found dead in a hotel room. Wonder what he died of. Oh, hang on. Yeah. Oh, well, never mind. And all this Scrum and all that kind of stuff. Just accept it. We can do one thing at a time. Well, some of us can do like 0.8 of a thing at a time, but and our brains are very bad at context switching. Just do one thing, and tell your boss, I don't do multitasking. I do one thing, maybe, if you're lucky. 6 ways to get your program to program in XXX. Reduce. I think fear of failure is probably the big point there. People don't do things because they're frightened of failing. So you have to reduce fear of failure. And in fact, the telling success stories is one of the things you do to reduce fear of failure. You can make a prototype at home. You can network with other people. We just don't bother. Just go off and do it. Find a venture capitalist and get them to give you lots of money, and then just go and do something. Yes, one thing people always surprised when I say this. Young people would come to me and they say, "So this job looks really interesting. Should I apply for this job?" I said, "I don't know." "Yeah, but the technique is fantastic. They're doing really, really great stuff." And I say, "So, well, have you looked at the balance sheet of the company?" "No. Why should I do that?" Well, and then I tell them, if you look at the balance sheet of a company and it's going down, then what they will do is cut costs. And they will cut all speculative stuff, they'll cut all their exciting projects, and they will concentrate on only the projects that earn money. And if you look at the balance sheet of a company whose profits are going up, they will be wondering what they do with their excess profits. So can we put some of our excess profits into exciting new projects and things? So look at the balance sheet. And in fact, when I left Ericsson, I was retired from them. They asked me to give a closing talk when I retired. So it turned out I'd worked for Ericsson for 2 periods. Erlang got banned and I quit. I formed a company. We sold the company for $150 million, and that was kind of fun, and I got a PhD, and then Erlang was sort of unbanned. I went back to Ericsson, and then I worked there for a few more years. And then when I retired, they asked me to give a talk. So I plotted the period when I'd worked for Ericsson against the share price. And there was 100% correlation. All the time when I'd worked for Ericsson, the share price had gone up, and all the time I was away, the share price had dropped and gone down. Yeah, I knew that's why I was a good guy. But the stock market didn't pick up on this, which was very strange. It was obviously the key factor in their balance sheet. Right. No, but look at it. I'm serious. Don't go work for companies whose balance sheet isn't positive, because they won't let you do anything fun, and they want to cut your costs all the time, and that's no fun. 3 general laws. Software complexity grows with time. It's because we build upon old stuff. Bad code crowds out good. This is Gresham's law. This bad money drives out good. In the old days, it had gold coins. If you could clip a little bit off the coin, save the shaving that you had clipped off, and you could still spend the coin and nobody noticed, you would make a profit. You collect all these little shavings. So slowly the gold coins got smaller and smaller and smaller. And the bad coins they tended to out-circulate the good coins because the good coins were taken out of circulation. They clipped little bits off the corner and kept the... So it's exactly the same with software. Bad software crowds out good software. Because you can't earn any money maintaining software if it hasn't got any errors in it. So, I mean, there's no money to be made by distributing good software. Make a ton of money by distributing bad software that needs a lot of maintenance. And bad code contaminates good code. Then you have to, how long have I got? Bear in mind the laws of physics and maths. A computation can only take place when the data and program are at the same point in space-time. Should remember that. Okay? Well, I mean, that can be anywhere. It could be you could have this client there and this data there and the program there. You can move it somewhere in between. This is why PHP is very good. Because it does everything on the server. When JavaScript goes wrong in client-server interaction, when you've got all the data you want in the browser and you're doing something, and then, no, I haven't got all the data you want. There's some other data that are off-site in a database. You've got to stop what you're doing, go talk to a database, get the answer back, and carry on what you're doing. But in that gap, all sorts of things can go wrong. So you maybe don't get an answer from the database, and maybe it doesn't reply. Second law of physics, causality, effect follows cause, and you never know how stuff is. You know how it was the last time it told you. So if you ask a database and say, how much money's Joe got? It's got $100. That doesn't mean to say that Joe's got $100. It means that the last time you asked the database said he had $100. He might have spent half of it since then. So you get the double spend problem in databases, which you can solve rapidly and easily using a central database, or you can solve in a very inefficient way using a blockchain. I mean, it'll only take like a day or something like that, and use half the world's energy up. And the second law of thermodynamics, entropy always increases. Entropy, how much longer have I got? 5 minutes, goodness. I'm going to have to skip over some things. The slides, I guess, will be on. You can read these later. The early Unix was pretty good. I was looking for a paper there to find this. I couldn't find it, but from memory it had like a 10 megabyte disk. Something like that. Somebody will correct me if I'm wrong. And once the programs are put on that disk, there wasn't enough room for lots of programs. So the programs that didn't get used were removed from the disk and thrown away. And because of Git, I mean, they weren't saved forever for posterity. No, they're just thrown away. And so entropy, there's something controlling entropy. This small volume of stuff just got better. It didn't just get bigger and bigger and bigger, and with more and more rubbish that sort of distracted you from the good stuff. Trust. Trust is important in software. I trust the software written by Robert Vierding, my collaborator when we developed Erlang. Robert's a really good programmer. Robert wrote X, therefore I trust X. It's transitive. I need a program to do X. I find X on GitHub. I don't know who wrote X. Can I trust X? I don't know. I'm quite often been very badly bitten by using software that I found on GitHub. It's going to save me a lot of time. Somebody's written this. Oh, I'll use it, right. Trouble with software. I chose some software to use. I won't name it, but given the choice between two projects on GitHub, I chose the one that had lots of test cases and a lot of documentation. It was wrong, of course, because not only was the test cases were wrong and the program was wrong. I mean, as somebody said, programs learn to pass their test cases. So if you write a set of test cases, and you will see errors in your program, you adjust the program so that all the test cases are passed. So they learn to pass the test cases. Once they've learned to pass the test cases, you're screwed, basically, if you don't write any more test cases. Actually, you shouldn't write test cases at all. There are more advanced techniques you can use than silly old test cases. Right, let's have a look. Responsible users' problems. 6 common problems that users have. Some of my friends, I mean, really good friends who are not computer people, they don't know how to delete files. When their computer fills up, they buy a new one because they think it's broken. And you put quite a lot of memory on these things, so it lasts about 2 or 3 years, and the disk's full, and then they get a new one. And they don't know what megabytes and megabits. And I had a friend, and I said, you know, he used up all his quota streaming a movie. And I said, so how much data? You know, he's got a data plan. I asked him, how many megabits a second, you know, is it to stream audio, and how many megabits a second? He hasn't a clue what these things mean. Totally. He's a very intelligent guy otherwise, I mean, but he's not a computer guy. They do not know what things are. Most users, I would say, including me, well, not me, I might try for 5 minutes. If the app doesn't work immediately, they give up. And actually, they don't Google for fixes, and even if they did, they wouldn't understand the answers. And they don't want to try the latest thing. And they don't want the UI to be updated. They just want it to work, for goodness sake, like it used to work. Oh, dear. Yeah. Wait a moment. Oh, yeah. Password, UI check. No, it'd take too long to tell that story. But tell it quickly. I wanted to reply to email. My wife said, you know, when I reply to an email, it goes into, it wants to start the Apple mail program, but I haven't installed it. I want it to go into Gmail. So I thought, well, that must be easy. I Googled a bit. Couldn't find out how to do it. Googled a bit more, couldn't find out how to do it. I tweeted. I got 20,000 Twitter followers. They said, try this, try this, try that. The first 2 or 3 methods didn't work. The third one did work, and I found out how to do it. It was completely unintuitive. And then I showed my wife, and she, Joe, you're a genius, you know. So how often do you click on a link, you know, a mail to link in your browser, and how much time do you think you've saved by doing this rather than cutting and pasting it? She said, well, I do it about like once every 2 weeks, maybe. And how much time have you saved by this little hack I've done? I don't know, 20 seconds? And how long did it take us to figure out how to do that? Well, about 4 hours. So I did the cost-benefit analysis, and it turned out that after 24 years, she would have saved some time. So that's why users don't like changing the user interface. The cost-benefit analysis of making a change to the system is so long that it's just not worth doing it. And anyway, if you do save 24 years, Google are going to change it in a year's time anyway, so the solution's not going to work in the future. So don't change the UIs. Oh, and could we make stuff that works, please? This is the next challenge. Making stuff that actually works. And if it doesn't work, that we know who to blame. When I'm streaming music and it doesn't work, I don't know if I should be nasty to Sonos. I don't know if I should be nasty to my ISP, or I don't know who's to blame. I want somebody to blame, and it should be legal. I take them to court, sue the bastards. Right. Yeah, and your non-technical neighbour, just tell them it's not your fault. Tell them I don't understand. It has a wonderful effect, you know. I'm a professor of computer science, and I go to my neighbours and say, I don't understand this stuff either. And they say, don't you? No. Then they feel good about themselves because they don't understand it. Because they think that, you know, the main thing about your neighbours, because you're a computer geek, they think you understand this stuff. And you just got to tell them, no, I don't understand. No, just tell them the truth. Nobody understands it. Not even the people who wrote it understand it. And tell them computers can't do everything. They get happy. Good, I'm gonna. How long have I got? 1 minute. Oh, crikey. Can I? Oh, well, we'll go fast. Yeah, just the headlines. Things can be small. We don't need gigabytes of code. The 4th kernel was like 24 kilobytes. We can write small programs. If we write small programs, we have a sporting chance we can understand them. The old truths: keep it simple, make it small, make it correct, fight complexity. Skip over that. Xandu. Anybody heard of Xandu? Yes, good. It's excellent. What we want to do, Xandu was Ted Nelson's idea of hypertext. There are no broken links. It's like the web, only better. There's no difference between readers and writers. The web is programmable and symmetric. All copyright and attributions are correct. You never lose any data. You've got complete knowledge of things. We really want to solve this what I call the 404 problem. The 404 problem, you know, you write a web page, it's got a remote link to something, it works fine, and then because they move that resource, it's broken. That is a design fault. It's a fundamental design fault. We have to solve that problem. Otherwise what somebody else does affects what we do. It breaks our stuff. We didn't ask them to do that. It should be completely symmetric. Solve the 404 problem, yes. Make sure we don't lose all our history. These are the problems I would, hopefully some of you guys will solve in the future. Make sure we don't lose all our history. Start measuring things in joules. I'm a physicist. It's joules, it's not dollars that are important. Minimize the number of joules in your program. And remember, we are responsible for the negative side effects of our technology. If we just happen to make everybody unemployed, we're going to have to find ways of giving them income. So, I mean, AI is fine and robots are fine. They should be used for dangerous and nasty jobs, but there will be consequences, and we have to be responsible for those consequences. What we can do, goodness. Unbreak the web, make it symmetric instead of asymmetric. Bring computation to the edge network. There's far more power in these little things we're carrying in our mobile phones than there are in the central servers. We should bring that computational power back to users and make sure it's easy to program, build applications that work together and are reliable, and make sure that we own our data and not big corporations. And basically, we should keep all our data on our own personal devices and only give it out on the need to know. We should ask them to send a program to process our data rather than sending our data to them, because we lose control of our data if we send it to them. What else have we got to do? Reduce entropy. Yeah. Throw away your old code, write less code, not more, and don't reuse code. Just write code that's correct. No edge cases, and just make sure it's okay. And a program that's not secure and cannot remotely controlled should not be written, so don't write stuff that you can't remotely control. So we've given millions of people supercomputers. They're all carrying them around in their pockets, so just let them use it. And it's your turn to do all that kind of stuff. I've been doing this for 50 years, and now I'm just telling people that it's your turn to go and do this stuff. So have fun inventing the next generation of computers. Thank you.